This training module is an introduction to the geographic, physiographic, and anthropogenic basin properties that are used to specify stormflows for the stream-basin analysis in the stochastic empirical loading and dilution model. This is training module 2.01a for the stochastic empirical loading and dilution model SELDM. This presentation has 14 slides and will take about 10 minutes. It was prepared by the U.S. Geological Survey in cooperation with the Federal Highway Administration. This training module has 5 learning objectives. At the end of this module, you should be able to identify and describe the geographic basin properties, identify and describe the physiographic basin properties, identify and describe the anthropogenic basin properties, discuss the ways that basin properties affect storm flows in SELDM, and identify the SELDM input forms used to enter basin properties. This diagram shows the components of upstream flows and highway runoff flows that combine to define the downstream flow statistics. The physiographic and anthropogenic basin properties affect the upstream pre-storm flow and the storm flows from the upstream basin and the highway site. The latitude and longitude determine the storm event and pre-storm flow statistics. The drainage area determines the amount of precipitation and stream flow that are generated for each event. The basin length, slope, and the impervious fraction or Basin Development Factor are used to calculate the timing of runoff from the upstream basin and the highway site. The total impervious fraction also is used to calculate the runoff coefficient statistics for the upstream basin and the highway site. The latitude and longitude are the geographic basin properties which are used to specify much of the hydrologic data used in an analysis. The latitude and longitude are used to automatically select regional precipitation, stream flow, and water quality data that are preloaded in the SELDM model. This is a map of the United States showing a hypothetical location at a latitude of 40 degrees and a longitude of -90 degrees. This map shows the U.S. Environmental Protection Agency rain zones as the black bordered and numbered polygons. The rain zone can be used to select precipitation statistics. This map also shows the discretized versions of the U.S. Environmental Protection Agency Level 3 ecoregions as colored areas on the map. The ecoregions can be used to select precipitation, stream flow, and water quality statistics in SELDM. This is a map showing the ecoregions, the rain zones, and the location of 2,610 National Oceanic and Atmospheric Administration hourly precipitation data stations. The latitude and longitude of the site of interest are used to rank the data collection stations by proximity to the site of interest. The location also helps you select upstream stream flow and water quality data by ecoregion or proximity to the data collection stations. The drainage area, basin length, and mean basin slope are physiographic basin properties. This is a schematic diagram of a basin with a map view and a cross-section showing physiographic basin properties. These same basin properties are used to define the characteristics of the highway site and the upstream basin. The drainage area is defined as the area of a basin measured in a horizontal plane that's enclosed by a topographic divide, such that direct surface runoff from precipitation normally would drain by gravity into the basin. Thus, it is the area of the basin footprint on a map, not the area of the land surface within the basin. At highway sites and in developed stream basins, the drainage area may be dependent on the storm sewer drainage system as well as the topographic divides. The basin length, also known as the main channel length, is the total distance in miles from the point of interest to the highest point on the basin boundary following the main channel route. The basin length may be much longer than the straight line length between the point of interest and the selected point on the basin divide if the channel is sinuous. The mean basin slope, also known as the main channel slope, is the average slope of the main channel of the stream upstream from the point of interest. The mean basin slope selected for SELDM analyses is known as the 1085 slope because it is calculated by determining the locations and elevations of points at 10% and 85% along the main channel from the point of interest to the basin divide, then dividing the difference in elevations in feet by the distance in miles between these points. The highway and upstream basin drainage areas determine the amount of precipitation collected. For highway sites, we are concerned with the amount of precipitation that runs off during each storm event. For the upstream basin, however, we are concerned with the precipitation that runs off during the storm and the surface and groundwater discharge from previous storms. In both cases, drainage area is a primary variable that controls the total flux of water through each area. This figure shows a hypothetical study site where Howard Brook crosses I-290 near Worcester, Massachusetts. The drainage area of Howard Brook, which is outlined in black and shaded red, is 1.34 square miles, and the drainage area of the hypothetical highway site, which is outlined in blue, is 6.4 acres, or about 0.01 square miles. Therefore, the upstream basin receives about 134 times the precipitation that the highway receives. If all other variables are held constant, increasing or decreasing the drainage area by 10% will increase or decrease the amount of runoff and pre-storm flow by an equivalent percentage. This hypothetical figure shows the importance of modeling the timing of storm flows within a runoff event. The diagram on the left shows the runoff hydrograph from a basin upstream of a site of interest and two potential hydrographs from that site. The hypothetical graph on the right shows the cumulative percentage of total upstream storm flow that occurs as the storm progresses. The diagram shows two potential runoff hydrographs from the site of interest, one with a short duration, duration 1, and the other with a longer duration, duration 2. This longer duration hydrograph may represent the effects of length and slope or use of BMPs that slow runoff from the highway. The site producing runoff for duration 1 only has 15% of the upstream flow for dilution. The site producing runoff for duration 2 has about 55% of the upstream flow for dilution. If the highway runoff quality is worse than the upstream water quality, then additional dilution will improve the water quality downstream of the highway outfall. This is a schematic diagram of a basin in map view showing selected components of the total impervious area. The total impervious area, abbreviated as TIA, is used to define the volume and timing of storm flow from the highway and the upstream basin. TIA is defined as the fraction, 0 to 1, or the percentage, 0 to 100, of contributing area occupied by anthropogenic impervious surfaces. TIA primarily consists of pavement and roofs. SELDM uses the impervious fraction to define TIA of the highway site and the upstream basin. TIA is an important explanatory variable for characterizing rainfall runoff transformations because impervious areas can rapidly convey precipitation towards the drainage channel network. Impervious areas generate runoff and can concentrate and convey runoff quickly. This picture shows runoff from paved areas and local rooftops entering a stormwater drainage system in Houston, Texas. In SELDM, the total impervious area, TIA fraction, is used to calculate runoff coefficient statistics and can be used to calculate the basin lag times. This is a schematic diagram of a basin in map view showing the selected components of the Basin Development Factor, BDF. The Basin Development Factor is used to define the basin lag time of the highway site and the upstream basin. The basin lag time is the time between the centroid of precipitation and the centroid of runoff. The Basin Development Factor is an index score from 0 to 12, indicating the prevalence of channel improvements, channel linings, storm drains or storm sewers, and the curb and gutter streets within the highway site and the upstream basin. To calculate the Basin Development Factor, divide the basin into equal thirds and give 1 point for each engineered drainage feature that is prevalent in each third of the basin. The Basin Development Factor criteria include straightening, deepening, and widening channels, paving channels, use of storm sewers, and curb and gutter streets. These engineered drainage features will quicken the runoff flows from the basin and the highway site. This diagram is a flow chart of the SELDM graphical user interface. The highway site and upstream basin forms are highlighted in yellow. The latitude and longitude are specified on the highway site form. The physiographic and anthropogenic basin properties for the highway site and the upstream basin are specified on their respective forms. In this module, we learned that the latitude and longitude are the geographic basin properties. The drainage area, main channel length, and main channel slope are the physiographic basin properties. The total impervious fraction and the basin development factor are the anthropogenic basin properties. The latitude and longitude coordinates provide access to preloaded precipitation, stream flow, and water quality statistics. The drainage area, main channel length, mean basin slope, total impervious fraction, and the Basin Development Factor control the volume and timing of storm flows. The highway site and the upstream basin forms are used to enter these basin properties.